what we're looking at today is starting off with inductive reasoning. Now, there's two main types of reasoning that we're going to be looking at. One of them is going to be inductive, and the other is going to be deductive. So we're looking at inductive and deductive reasoning, and there's one big difference between the two. Inductive reasoning is a conjecture. A conjecture is let me restart that sentence. A conjecture is an unproven statement that is based on observations. You use inductive reasoning when you find a pattern in a specific case and then write a conjecture for the general case. So we could write that whole thing out, but let's look at it. So first it says a conjecture is an unproven statement. And inductive reasoning is when we find a what? Pattern in a specific case and then write a general case. So really, inductive reasoning, we're looking for a what? Pattern. We're looking for a pattern and then writing a case or a statement, a conjecture based off that pattern. So inductive reasoning is really, we're using reasons or reasoning to figure something out based off of a pattern. A pattern that we expect to occur. Based off a pattern that we expect to occur. So, again, this is all based off of observations because patterns are what we see. It's something that we see and something that we observe, yes? Yes, so kind of like at a call cord football game, if we see a flag thrown, we know it's on who? Probably call cord, yes, because that's how it goes most of the time. Because, I mean, we've seen the pattern, we expect it to occur, yes? Does that mean that it's true that that's always going to happen? Well, no. It's just something that we've seen and we see it to occur. It's just a pattern we observe. Doesn't mean it's true, it's just something that we have observed and it repeats. So when we look at this here, these circles, now obviously the printer is not strong enough to print the shaded region onto y'all sheets. Even the old printers that were a little bit better than the ones we have now didn't get the shading either. It's quite faded. So when we look at this here, we have three circles that are shown to us. In figure 1, half of it's shaded. In figure 2, a fourth. In figure 3, we have a sixth. So what do we expect to occur if we had the next one? So an eighth. 2, 6. 1, 2, 3, 4, 5, 6, 7. Okay, I did too many. We actually had it right before I'd added the extra one. There's half, half. 1, 2, 3, 4, 5, 6, 7, 8. And we're saying only one of those would be shaded, yes? Because we have a half, a fourth, a half, a fourth, a sixth, an tenth, an eighth, and then the next one would be probably a tenth, because it's kind of going in even number. And that's it. Because we saw the pattern. It's going a half, a fourth, a sixth, so we would say an eighth. And that's it. That is inductive reasoning. We're looking at what's given, seeing the pattern, and continuing it. We're used inductive reasoning. So we have a star, and we see one piece here is not shaded. And then the second one we have 2, and then the third one we have 3. So what's going to happen to the because we'll have that one shaded, the center would still be shaded, and then we just got one of the other sides. And it's also interesting to note that it is going counterclockwise. The way that the unshaded ones are going, because we started in the bottom right, then we had bottom right and top right, bottom right, top, middle, top. Well, heck, if I actually shaded it right, because I just reshaded the third one. Yeah, we'd leave 4 of them open. Why do I feel like I said that and then just went on and shaded the extra one? Yeah, I'm glad I re-looked at that, because I essentially just repeated what they had in the third one. So we should only have one shaded in the 4th step. Now, if we did it one more, what would it be? Right, it would just be the middle that would be shaded, because we'd made it all the way around if we wanted to do one more. Any questions on number 2 before we look at number 3? Well, number 3, we start out with one circle. Then we have 3. And then we have 6. All right, so I'd have 1. I'd have 2 underneath it. And this here would give me the one I have. Then the next one would have 4 underneath it. We're just adding an additional row with one more. Yeah, 10. Yeah, so 1, 3, 6, 10. Because we added a row at the bottom, yes? Because we had started out with a single one.
I thought we had 3.
We added 2. Here we added 3. So to add another row, we would add 4. But what would the next one in the sequence be? 5. So it'd be 15. Questions on this here? Describe how to sketch the 5th in the pattern, and then sketch the 5th. So we start out with a 1, 1, 2, 3, 4, 5, 6, 7. So we'd add a box to the left and to the top. Yeah, so we'd have 1, 2, 3. Well, that would be what we had originally, 4. We would need one more. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. We start out 1, 3, 5, 7, 9, because what are we doing? We're adding 2 more squares, one to the left and one on top. And that's it. Any questions on this here? We're ready for the next one. Making and testing a conjecture. Now, when we have shapes or pictures or diagrams that we've had so far, it's kind of easy to see what the pattern is. Sometimes it won't be as easy. So when we look at this here, numbers such as 3, 4, and 5 are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. Let's start with 3, 4, 5. 3 plus 4 plus 5. 12. Okay, well, any big revelations coming with this here? Well, not too much. We only have one example, yes? So, I mean, another one I could pick would be, so 5 plus 6 plus 7. Well, 5 plus 6 is? Plus 7 is? 18. We seen anything yet? Kind of not really. So 7, 8, 9 would work. Eight plus 9 is? 17 plus 7 is? 24. So I'm just adding those 3 together. Now there is a unique property that these 3 numbers have with their sum. They're all divisible by 6. So give me another just random set of 3. They don't have to be after 9. Well, they just go bigger than 9 as the starting number. 11 and 12 is 23, so 36. I'm going to pick just a set. Let's say 78, 79, and 80. 70 and 70, so 78 and 79 would be 7, carry the 1, 157. Plus 87. $237. If you have a calculator, I'll go on and grab one if y'all don't. Plus 79 plus 80 is 237. Well, 237, if we divide it by 6, it doesn't come out evenly. So those being divisible by 6 is a good idea, but this one doesn't work. Now, if I try 4 plus 5 plus 6, 4 plus 6 is 10, plus 5 is 15. So with those 3, it didn't quite work. But there is a unique property with this. Odd plus odd, we do that, or even plus odd plus even. Because divisible by 6 was a good path, maybe not 6. Because what's divisible by 12? Well, 4 is, yes? 3 is divisible by 12, so it'd be 3 and what? 3 and 4, okay. That's interesting. What's 18? And what's 18? Or 24? 3 and 8. That's a little weird, isn't it? 3 is common in all 3 of those, yes? What about the other number? Does it show up there? Because we said the first one was what, 3 and? Did we use 4? Well, 3 times 4 is? 3 times 6. 3 times 8. Let's see here. Let's say 79 times 3. 3 times 9 is 27. 3 times 7 is 21. So really, we can say that any 3 consecutive integers is 3, or consecutive integers, we would say sum is 3 times the what? Middle number. And that'll work every single time. And how do we find that? We just did a whole bunch of tests to see if it would work. Now, mathematically speaking, this wouldn't hold up in a scholarly type of way. Because again, how many times do I need to show that something's false? Once. Here I showed that it worked 6 times, yes? But could there be a chance that one of them, there's one out there somewhere I didn't test that does work? Yeah. So we would have to do it in a more using variables, because if I can show it, it's I've lost the name. I think it's because we can do the int plus 1 proof. If I can show it for that it is true for n, if I can assume n is true and I can show that the int plus 1 case is true, the one after it, that means any case that does work for n, the one after it would work as well. So I can prove it for all. Because no matter how big I gotta make n, the one after it is true as well. So I proved it for everything. So they do it in variables. But questions on this here? You won't have to do the nth case. Make a test and a conjecture about the product of a negative integer and a positive integer. So give me a negative integer. Give me a positive integer. 3. I think you said 4. 4. We'll use 4 in the next one. So what's negative 2 times 3? Okay. Give me another negative integer for the next one. What is negative 22 times 4? Well, I think you already know what this is, or should. What do we know about the product of a negative integer and a positive integer? A negative, because as we've always said, a negative times a positive is a negative. The product of a negative integer and a positive is always negative. Now we could say always a negative integer or always negative. Either one will work. Questions on this here? Pretty good with this here. Make and test a conjecture about the sign of the product of any three negative integers. So give me three negative integers, or three negative numbers. Huh? -5? I would do -5 times -4. And -3 times 20 is negative. I just picked 2, 4, 10. -2, -4, -10. Well, -2 times -4 is 8. 8 times -10 is negative. -80. Y'all see a pattern? Because, I mean, they all end up with a 0, but that's just, well, let's try something different. Let's say -2, -3, -4. Well, -2 times -3 is 6 times -4 is -24. What are you going to say? No. Yes. They're always negative. Because a negative times a negative is a times a negative is a negative. So it worked out that they were all even, but really the big thing is that they're negative. Because I could have picked probably 3 odd numbers, and it would have given me an odd. So I could say -3, -7, and -11. Well, -3 times -7 would be 21. Times -11 would be -231. Yes. Which would be an odd number. But it still holds true that it is negative. So the product of 3 negative integers is always a negative. And if you just wrote always negative, I'll take that, that's fine. It's saying the same thing. Any questions on this here? And again, if you're having trouble seeing the pattern, just keep trying. Keep trying more and more and more to see if it works. Are you ready for the next one? Make and test a conjecture about the sum of any 5 consecutive integers. I just picked the first 5 numbers. 1 plus 2 plus 3 plus 4 plus 5. 1 plus 2 is 3, plus 3 is 6, 15. What else could we have? 7 plus 8 plus 9. 5 plus 6 is 11. I would do plus 9 is 20, 27, 35. Anybody have a guess so far? They're divisible by 5, yes? So what's 15 divided by 5? Middle number's 3. 35 divided by 5. Well, integers are any positive or negative number, yes? So what about -2 plus -1 plus 0 plus 1 plus 2? because negative 2 plus 2 is, negative 1 plus 1 is, so we're left with plus 0, so it is 0. Let's see if that still works. 0 times 5 is, let's start off with negative 5 plus negative 4 plus negative 3 plus negative 2 plus negative 1. Well, this is the same as the first. It's just what? Negative, isn't it? So this should equal negative 3 times 5 is negative 15. So it still holds true, doesn't it? The sum of any 5 consecutive integers is always 5 times the middle number. That's kind of interesting, isn't it? Any questions on this here? Counterexample. Anybody have a guess at what the definition for counterexample is? That is counter. If we counter something that is the what? Opposite, or shows that it is false. To show a conjecture is true, you must show it true for all cases. If we want to show it's true, we have to show it's true for every single possible case. You can show that a conjecture is false, however, by finding just one counterexample. A counterexample is a specific case for which the conjecture is false. Well, that kind of makes it hard to prove something's true because you have to show it for every single case that it does work. So a lot of times what they'll do is I will set it up or say, like the last one we had, the sum of any 5 consecutive numbers we saw is the middle term times 5, yes? Okay, I would change the statement and do something that would be probably a little more rigorous than this, is saying that the sum of any 5 consecutive integers is not equal to the middle number times 5. Well, I can show one case where that's false, yes? Now I've proven the other statement, or that's essentially what they would do, especially in trying to prove something's true. I negate it, show that the negation is false, and when we negate something, does it means that if I turn it back, since the negation of a statement's false, it means the actual statement is true. And that's what they'll do a lot of times with proofs. A student made the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. The sum of 2 numbers is always more than the greater number. So 2 plus 3 is equal to 5. So the semicolon is 5 greater than 3, the bigger number? Yes, okay, so that would not be a counterexample. So thinking about any number, someone think of one that wouldn't work. Okay. 11 plus 12 is 23, greater than the bigger number, which would be 12. Does it work there? Is 23 greater than 12? Okay, so that still works. Okay. 46 plus 2 is 48. Is 48 greater than 46? Yes. Oh, we don't have to use 0 and 0. Give me a different number. Huh? What's 0 plus negative 1? Is negative 1 greater than, so which one's going to be bigger? Is negative 1 greater than 0? There's our counterexample. Really, we didn't even need 0. I could have said 46 plus negative 1. This would be, is 45 greater than 46? So really what was 0 would have been a big key, because 0 would have worked with any of them. Because 0 plus 1 is 1. 1's not greater than 1, because it'd give us the number itself. So really, if we wanted to make this a true conjecture, the sum of two numbers is always, well, we wouldn't say the sum of two numbers. We would say the sum of two natural numbers, or the sum of two positive numbers. Because we can say positive because 0 is neither positive nor negative. Do you all get that? Because 0 is not a positive number or a negative number. It doesn't fall into either category. The conjecture that we have here, the absolute value of the sum of two numbers is equal to the sum of two numbers. So I'll just throw an example up here. So the absolute value of, say, 2 plus 3 is equal to the absolute value of 5, which is equal to 5. Yes? Well, 2 plus 3 is equal to 5. We came out with the same number, yes? And that's what it's saying. The absolute value of the sum of two numbers is equal to the sum of those two numbers. What would be a counterexample to this? So the absolute value of the sum of two numbers, that's that there, is equal to just the sum of two numbers. It did an absolute value for one, and then the other side is just without it. Well, negative 1 plus 2 is 1. The absolute value of 1 is 1. Now, the other setup would be negative 1 plus 2, which is 1. Are they the same number? You're on the right track, but maybe we need to do it a little bit differently. So what else could we try? Negative 2 plus negative 2 is negative 4. The absolute value of negative 4 is positive 4, yes? Now the other side would be negative 2 plus negative 2, which is are these the same? No. So there's our counterexample. Now, Briar, I think it was one you said was negative 1 and 2. You were on the right track, but if I said 2, instead of negative 1 and 2, I said 1 and negative 2, it would have worked. Because 1 plus negative 2 would be negative 1. The absolute value of negative 1 is positive 1, yes? But if I just add them together, I wouldn't get 1, I would get -1, because we have that opposite sign. Questions on this here? And I believe this is the last one, or one of the last ones we're looking at, second to last. The value of x squared is always greater than x. So if I did, say, 2, well, what is 2 squared? Yeah. Well, 4 is going to be greater than 2, yes? I put it in parentheses just so we know that that's how it works out. There's a lot of times when we plug in a number, if there's a sign or something out in front of it, so if it was, say, -x squared, we know to square the term and then apply the negative. Especially if we said -2 squared, and you type this in the calculator, is if you just type -2 squared without the parentheses around the -2, it'll tell you that it's -4. Well, what we want is -2 times -2, yes? We know a negative times a negative is always positive. Because when you plug it in without the parentheses in the calculator, it sees -2 times 2. It's going to square the 2, not the negative. It doesn't see those as being attached. So we can put the parentheses around it. Well, let's go on and finish this. -2 squared, we said, is 4 greater than -2. Yes. So positive numbers work, negative numbers work. What else could we try? Well, 0 squared is 0 greater than 0? No. We could also do fractions. 1/2 times 1/2. Does anybody know it? It would make it 1/4. Because we can square the top and bottom. 1 squared is 1. 2 squared is 4. And we're saying that this would be greater than? Is 1/4 greater than 1/2? No. So fractions and decimals, when we square them, they actually get smaller. So 0 or fractions, either one of those would work. Do I need to include both? How many do we need? 1. As soon as we got 0, we're done. The sum of two numbers is always greater than their difference. So if we set it in a general case, A plus B is going to be greater than A minus B. Is going to be greater than 2 minus 1. So 2 plus 1 is? 2 minus 1 is? Okay, that's true. What's a case that wouldn't work? Yep. Zero plus 0 is 0. 0 minus 0 is? What if I tried a negative? Because it didn't restrict negatives, did it? So 2 plus negative 2 is? Well, here a negative and a negative make a. 0 is not greater than 4. So 0 works a lot of the times. Negatives also work. So also be careful, especially on the wording of what they specify. And that's it. Homework is on page 74, problems 3 through 5, 7, 9, 10, 12,